In this video, we will look at another definition of derivative example. So I'm going to up the difficulty a little bit this time compared to the example that we did in the last video. Let's let the function g of x be this rational function, x minus 3 over 4x plus 1. In part A, I want to find g prime of x with the definition of the derivative. So remember, that means no shortcuts. If you've seen derivatives before, we can't use derivative rules to do this. We got to use the limit definition. All right, so we want g prime of x. So the limit definition says that this equals the limit as h approaches 0 of g of x plus h minus g of x over h. And now we can evaluate g of x plus h. If I plug x plus h into my function where the x is, on the numerator I will get x plus h and then minus 3. In fact, let's put this in a different color. So the x plus h is what I'm plugging in. So I get x plus h minus 3. On the denominator, we will get 4 times that x plus h instead of just times x, and plus 1. So g of x plus h is this fraction. Notice again, all we've done is I've plugged in x plus h wherever the x was in my function. All right, so then I have to have minus g of x. G of x we know is just x minus 3 over 4x plus 1. So g of x matches up with this. And we can't forget that we have that h in the denominator. So that h is still there. All right, and whoops, I made a cardinal sort of rule break. I forgot to write a limit in front of this. Okay, so let's scooch this over. Let's make sure that we include that limit. So I have to keep writing this limit in front up until the point where we actually plug in the number. All right, so we have a limit as h approaches 0. And I have a fraction minus a fraction. So we have x plus h minus 3 over, if I distribute the 4x plus 4h plus 1, minus the other fraction is x minus 3 over 4x plus 1. And to subtract two fractions that have different denominators, we have to get a common denominator. So let's multiply this first fraction, top and bottom, by just 4x plus 1, the other denominator. Same thing on the bottom, 4x plus 1. And then I multiply the second fraction, top and bottom, by the first denominator. So 4x plus 4h plus 1. And then same thing on the bottom, 4x plus 4h plus 1. And I cannot, or I don't want to forget this h that's on the denominator of all of this. All right, so now let's start to multiply this out and simplify. Okay, so I'm giving myself some more room. I've just copied this whole thing down. And one thing that you might notice is, so we had this h on the bottom, but having h on the bottom is the same thing as writing h over 1. And that'll show up in the next step. This is something that we've seen before when we did difference quotients and simplifying them. Okay, so let's see. We got the limit as h approaches 0. And now, when we multiply these first two fractions, I have to distribute in the numerator. So I'll do x times 4x. So that gives me 4x squared. Then let's do h times 4x. That gives me plus 4xh. And then let's do the minus 3 times 4x. That gives me negative 12x. Okay, so now we got to do the same thing, except we distribute to the 1. So that'll give me plus x plus h minus 3 when we distribute to the 1. And then all over that denominator. And let's actually just start to combine it into one big fraction. So the denominator, I will actually not multiply out. I'll keep it as 4x plus 4h plus 1 times 4x plus 1. And I'm doing that deliberately because in a difference quotient problem like this, ultimately, I know from experience now that this h on the bottom needs to cancel with something on the top. But it would need to cancel with something in the numerator. It would need to cancel with something here. Not in this denominator portion, not in 4x plus 4h plus 1. and so on. It won't cancel with anything there. And that's because when you divide by h over 1, that's the same thing as multiplying by 1 over h. So if this h is going to cancel with anything, it'll be the numerator of this fraction. So for our purposes, it's actually better not to multiply out the denominator, because if we do, it actually makes it harder to see what cancels later. All right, so now there's a negative sign. It needs to be there. And that means I'm subtracting everything that comes after the negative sign. So let's make sure I don't forget that. Let's put a big bracket after the negative sign. Okay, and now let's start a distribution. Okay. All right, so I'll do x times 4x, x times 4h, x times 1. So x times 4x, that's 4x squared. And then we get plus 4xh, x times 1 plus x. And then we have to distribute the negative 3, so negative 12x, negative 12h, a little bit more room, and then negative 3. All right, so we have the limit as h approaches 0 of this whole thing. But in the numerator, a bunch of terms are going to cancel. So when we subtract, this 4x squared and that 4x squared will cancel. The 4xh here and the 4xh here will cancel when we subtract. Let's see, negative 12x, they'll cancel when we subtract. The x and this x will cancel. And one more thing, the negative 3 and that negative 3 will cancel. What we are left with is this h. So what we're left with in the numerator is we get h minus negative 12h. So double negative becomes a positive, and then we get 13h. So 13h all over 4x plus 4h plus 1 times 4x plus 1. And now when I multiply by 1 over h, I can put that h in the denominator. But now I see yet another cancellation. This h on the top and the bottom have been factored out, so we can cancel them. And after we cancel them, the thing that was stopping us from plugging in from the get-go is gone. That was this h that we had in the denominator. But now that that's canceled away, I'm actually good to plug in. So I can stop writing the limit, because now I'm plugging in. We get 13 on the top. On the bottom, we get 4x plus 4 times 0 plus 1 times 4x plus 1. So we're only plugging in the 0 where the h is. And simplifying this, this is 13 over 4x plus 1 quantity squared. All right, so this is our answer. This is what the derivative of our function was. So g prime of x equals this. Okay, so part B, a related part, is now find the instantaneous rate of change, that's IROC, of g, of the function, at x equals a negative 1. So if I want the instantaneous rate of change, IROC, of my function of g at x equals negative 1, that means take the derivative, so take g prime, and just plug negative 1 in where the x is. If we do that, we get 13 over, in the denominator, we'll get negative 4 plus 1 squared, which is 13 over negative 3 quantity squared, going to be positive 9. So the instantaneous rate of change at that point, at x equals negative 1, is 13 over 9. Alrighty, so in terms of our goals for this section, we have defined the derivative of a function in this first way, where we take the limit as h approaches 0. In a later video, we will look at another form for the definition of the derivative, and that'll be this form in part B.